Okay, we're going into chapter two. Chapter two is a little bit vague. We're going to skip around a little bit in it. But chapter two is all about the how the atom works, behaves, and we're going to look at what's called the quantum model of it. But before we do that, let's talk a little bit about electrons. So electrons, as we know, we learned when we talked about protons, neutrons, and electrons, they are very small pieces of matter. To give you an idea, the number of electrons in a single speck of dust is higher than the number of people who have ever lived on the Earth. So you can see how small they are. Because of their size, we can't directly observe them. So we have to look at changes in behavior of certain things to kind of come up with the electrons actually doing, maybe where the electrons are. And so right now we're going to start by looking at how we determine the behavior of our electrons. This thing called quantum mechanics, or the quantum mechanical model of an atom. This explains the behavior of the electrons. So this is going to be very brief right now. We're going to get more into detail on this, but this model explains the manner in which our electrons exist and behave in our atoms. Okay, we're going to look at it in a couple different ways. We're going to look at it in terms of light, or light wave, which is energy, and what happens when we focus on light. That's going to help us look at the characteristics of the electron. And this helps explain the chemical and physical properties of our different states of matter. So one thing that's going to seem sort of different is that we are not going to look at the electron just as one little piece of something. We're going to look at it in terms of what we call an electron cloud. And I'll show you what I mean by this. I get my pen to work here. When we drew the atom before, so let's say here's our atom, here's our nucleus, we saw, and I drew an electron. So we know the electrons are outside the nucleus in the atom. However, that's just showing that the electron is in one specific position. And that's not the case. We're going to look, because they're moving constantly, we're going to look at what's called an electron cloud. So we're looking at a probable area that our electrons are in. And we'll get more into detail on that as we go on. Okay, a little bit more about what the quantum mechanical model of an atom tells us. It's super important. It does form the foundation of all of our chemistry, with the basis being your periodic table. This actually allows us to see why the periodic table is formed the way it is and the trends that it has. It describes for us the behavior of our elements in regards to how they bond in their chemical bonding, the colors, and their size. It also predicts atomic properties. Atomic properties are directly related to the behavior of atoms, are things like, why is it a metal? Why is it a non-metal? Why does one element gain electrons? Why does one element lose electrons? Why does one element only gain one electron and another gains two? Some elements are very reactive, some are not. Some of them, like our noble gases, are inert, which means they're not reactive at all. This all is dependent on our electrons in the quantum mechanical model of our atom. Okay, so step one to understanding the electrons is the energy of the electron in regards to light. All right, we know that light moves in waves. So I'll explain that a little bit more in a minute, but light is a form of what we call electromagnetic radiation. There's lots of different types of radiation, and we'll go over different ones as the semester proceeds. Okay, so what this is saying is that light moves in what we call oscillating waves. And it moves at a speed of 3.00 times 10 to the 8th meters per second. This is a constant that we're going to use. And the symbol for it is c, lowercase c. C represents the speed of light. Let's look what I mean by oscillating waves. So light moves in a field, but And when we say it moves in waves, it's moving in waves, just like that. So electromagnetic radiation can be described as waves in an oscillating electric and magnetic field. And they are perpendicular into their planes. And you can see that here. The red is up and down, where the blue here is going side to side. All right, so without going into a whole lot of detail of any more on the waves, let's just talk about the wave and how it's made up. So we know that, again, light is moving in waves. And so let's talk about the wave. The waves have what we call a wavelength and amplitude. The amplitude is this. It's the height of the wave. The wavelength is determined by looking at two different bumps, we'll call them. And so we're going to look at this, the top of this one and the top of this one. The distance between those two is the wavelength. So it kind of tells us, you know, how long it's going to take for the wavelengths to go from top to bottom. All right, so here we have the peak. It's also called the crest. And then down here we have the trough. You can measure wavelength from peak to peak or from trough to trough. Either way, it should give you the same thing. Okay, so by definition, amplitude is the height of the wave, and the wavelength is the distance covered by one full wave. So crest to crest, or peak to peak, and trough to trough. Wavelength and amplitude are independent properties, so they're not based on each other. You can have similar wavelengths but different amplitudes. The wavelength of light actually determines its color. This is an intensive physical property. So there's going to be certain wavelengths that will give you different colors. And here's just some examples of showing that. Amplitude is where we get intensity. So that helps us see brightness. So as your amplitude increases, as we see here, the taller amplitude versus a smaller, you're going to have a brighter color, but the wavelength will determine the actual color. Now, wavelength, or the color, excuse me, let's go back to color for a minute. Wavelength does determine the color, but so does something called frequency, and we'll talk about frequency in just a second. White light is a mixture of all the colors of the visible spectrum. So the colors of the visible spectrum is red, orange, yellow, green, blue, indigo, and violet. When an object absorbs some of the wavelengths of white light, so I want you to see that here. You see this white light? So it's like a laser white light that's hitting this prism. White light will reflect that light and show different colors. And it happens at certain wavelengths and certain frequencies. So you see here, then we have a reflection of our visible spectrum, of those 7 colors. Okay. So use the word frequency. Wavelength and frequency both together determine the color, but what is frequency? Frequency is the number of waves that pass a point in a given period of time. So it's the number of waves per cycle. We have, our frequency is measured in what we call hertz or per second, cycles per second. So these are the units for that. The total energy of our light and what's happening here is proportional to the amplitude and the frequency. The larger the amplitude, the more force it has, which makes sense, right? It's got a larger hill to climb and then release. The more frequently the waves strike, the more total force there is. Okay, so let's look at the relationship between wavelength and frequency. There's a mathematical relationship, and here it is. So let's talk about what this is. This, our little cursive V, this stands for your frequency. Frequency is equal to the speed of light over wavelength. So frequency is equal to 3.00 times 10 to the 8th meters per second over wavelength. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. So we can use this to solve for one or the other. It's kind of as far as we're going to go with the math in this chapter. All right, so here we go. Couple things. Wavelength is usually represented in nanometers. Okay? And remember, for every 1 meter, there is 10 to the 9th nanometers. Okay, so that's going to be important. Okay, so here we have calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th per seconds. All right, so I'm going to go use my little equation here. So I know that frequency equals the speed of light over wavelength. So if I rearrange this, I have wavelength equals the speed of light over frequency. So I'm going to go ahead and plug it in. We know the, So I have 3.8 times 10 to the 8th meters per second over my frequency, and they give it to us there. So we have 4.62 times 10 to the 14th per second. So seconds cancel, right? Let's do our math. And we get 6.49 times 10 to the negative 7th, and my unit here is meters. It wants it in nanometers, so I can do simple conversion. For every 1 meter, there's 10 to the 9th nanometers. Okay, so then, you don't have to do much math here. You're just gonna, when you multiply exponents, you add them. So that gives me 600, or actually you can put it like this. You get 6.49 times 10 to the 2nd nanometers, which is the same thing as 649 nanometers. All right. So that would be my answer. And here, let's look at this one. Here we're given a wavelength, and it's asking to calculate the frequency. So I'm going to, base it off this. But I know my wavelength needs to be in meters here. And why is that? Because our speed of light is in meters. So if I have speed of light over wavelength, those units need to match. So I'd make this pretty simple here. Anytime I'm given nanometers and I need to convert it to meters, even though it's not correct scientific notation, you can just add that times 10 to the negative 9th. Okay, so I'm going to have frequency is equal to 3.00 times 10 to the 8th meters per second divided by 515 times 10 to the negative 9th meters. Oops, this should be meters. Do that math. You should get a big number. Frequency always is. So you get 5.83 times 10 to the 14th, and it's going to be per second. That's as far as we're going to go with calculations right now. We're not going to go into the energy calculations. So just being able to go between frequency and wavelength is all I expect at the moment. So let's look at this. Here's our electromagnetic spectrum. Visible light, this is the colors you see. So if I have an object, it's absorbing white light, and it absorbs it at, let's say, 575 nanometers, then you're going to see this green color. If it absorbs it at 700 nanometers, then you're going to see this red color. So that's what I mean by that. There's different types of radiation. Visible light falls between what we know as infrared or ultraviolet. So the highest form of radiation is the gamma ray, and it's actually the most destructive. It's the one you really don't want to be around. This would be on a extreme sense. This is what you get from like your atomic bombs or bombs in general. And then X-rays you're all very familiar with, ultraviolet, the sun, infrared, microwave, and then radio waves. Radio waves are very low in energy. That's why we're able to have them in our car, right? So even though you're playing the radio all day, you're not getting very much radiation that will harm you. Radiation that will harm you is the ones that are higher energy. Higher energy has a higher frequency and a shorter wavelength. You'll notice here all of our wavelengths are in nanometers, and all of our frequencies are big numbers like we were just looking at, 10 to the 14th. And hertz is the same thing as per second. Okay, visible light falls between 400 to 700 nanometers. So it's a very small part of the electromagnetic spectrum. Shorter wavelength, higher frequency light has higher energy. Just a recap of what we just said. Radio waves have the lowest energy. Gamma ray light has the highest energy. The higher the energy, the higher the damage that can be caused to an individual. So if we look at terms of biological molecules or you don't want to be anywhere near where there's gamma rays. Waves have a couple different properties that we're just going to look at briefly. And one of them is what we call interference. The interaction between waves is called interference. Okay, there's two types of interference. There's constructive interference, and that is when waves interact, so they make a larger wave, so they come together. Right? They're kind of on the same pattern, they're in the same phase, so they can come together and make a bigger wave. Destructive interference is where they interact, so they cancel each other out. So they're known to be what they call out of phase. Okay.